Welcome to the Explainer. Today we are jumping right into a really elegant and honestly powerful technique for dealing with second-order differential equations. It's called reduction of order. So, picture this. You're deep into a problem. You've got a second-order DE, and you found one solution. Maybe you just spotted it or you used another method, but now you're stuck. You need that second solution to build the general solution, and you've hit a wall. Sound familiar? It's a super frustrating place to be. But what if the answer was right there in front of you the whole time? I mean, what if that second solution you're looking for was kind of hiding inside the one you already have? That is the absolutely brilliant idea behind reduction of order. Okay, so let's get into our first section, the one solution problem and a clever guess. This is where we lay the entire groundwork for how this thing works. So what is it really? Well, reduction of order is a way to find a second linearly independent solution. And that's key. It means the new solution isn't just, a constant times the first one. The name says it all, really. We find the second solution by literally reducing a tricky second-order problem down to a first-order one, which is way easier to handle. Now, here it is, the one single idea that makes all of this possible. It's this incredibly clever guess. We just assume that our second solution, y2, is nothing more than our first solution, y1, multiplied by some new mystery function. Let's call it v of t. This one assumption, this is the key that unlocks the whole puzzle. So we have this great guess, but how do we actually use it? Well, there are basically two ways to go about it. Think of it as our toolkit. We've got a step-by-step recipe and a direct formula. First up, let's talk about the recipe. This is your reliable go-to substitution method. You start with a guess, y equals v times y1. Then you just grind it out, differentiate it twice to get y prime and y double prime. Then you plug all of that stuff back into the original equation. And here's where the magic happens. Things start canceling out in a really beautiful way. The whole equation reduces, and you can solve for that v of t. Then, on the other hand, you've got the direct formula. And yeah, I know, that looks like a lot. It's a little intimidating. But all this formula really is the final result you'd get if you use the recipe on a generic second-order equation. It's a massive shortcut that can get you to the answer way faster if you know how to use it. So which tool do you pick? Let's think about it like this. The recipe is like a good old-fashioned wrench. Yeah, it takes a little more elbow grease, but it's safe. It really helps you understand what's going on under the hood, and it's perfect for when the algebra gets a little messy. The formula? Well, that's your power drill. It's super fast, but you gotta be careful. It only works if your equation is in standard form, and it's really easy to slip up on an integral somewhere. All right, that's enough theory. Let's actually put this toolkit to work and see it in action with a few examples. Okay, this first one solves a classic mystery. Remember from constant coefficient equations with repeated roots, how that extra t just kind of appears in the second solution? Well, let's find out exactly where it comes from. We've got this equation, and we already know one solution is y1 equals e to the rt. So let's follow the recipe. We set y equal to v times e to the rt. We take the first and second derivatives, it's a bit of product rule fun, and then we plug all three of those big expressions back into the original dE. Now it looks like a total mess at first, but just watch. And this is just perfect. It shows you the real power of the method. After you distribute everything and collect all your terms, the whole thing just collapses. The terms with v vanish, the terms with v prime vanish, and you're left with this incredibly simple equation, v double prime equals 0. And I mean, solving v double prime equals 0 is about as easy as it gets, right? You integrate it twice, that gives you v of t as some constant times t, plus another constant. We only need one new solution, so we can pick the simplest case. Let's say the first constant is 1 and the second is 0. That gives us v of t equals t, and there it is. The second solution is y2 equals t times e to the rt. Mystery solved! All right, for our next example, let's break out the power drill. Here we've got an equation with variable coefficients, and we're told that one solution is t to the negative 1. This is the perfect time to use that direct formula. But wait! Before you even think about plugging things into the formula, there is one absolutely crucial first step. The formula only works if the equation is in standard form. That means the coefficient on y double prime has to be 1. So first things first, we have to divide the entire equation by 2t squared. Seriously, forgetting to do this is probably the #1 mistake people make, and it'll give you the wrong PFT and throw your whole calculation off. Okay, now that it's in standard form, we can see that our P of t is 1 over 2t. And from here, it's just about working through the steps. We calculate that exponential term, we set up and solve the main integral inside, and then we combine everything. We can ignore the constant fraction out front, and boom, we get our second solution. y2 equals t to the power of 3/2. For our last one, let's tackle a problem where the substitution method, our trusty wrench, really shines. We're given the solution y1 equals e to the t. And just looking at it, you can tell the algebra is going to be a little more involved this time. So we do the same dance, we substitute y equals v times ut to the e, and its derivatives, we plug them in, we cancel out the e to the t that shows up everywhere, and we carefully group our terms. And what do you know? Just like before, the term with just v in it completely disappears. Our second-order dE reduces down to this new, much simpler first-order equation for v prime. Now, we can solve this new equation for v prime using separation of variables. Then, to get from v prime to just v, we have to integrate again, and this time it actually requires integration by parts. So after all that work, what do we get? A surprisingly simple polynomial. Our second solution, y2, is just t plus 1. So after all that, after seeing those examples, what is the big idea here? What is the new superpower you've just picked up? The superpower of this method is really, really simple. It takes what looks like an impossible second-order differential equation and turns it into a solvable first-order one. All it asks for is one solution to get started. You give it that, and suddenly the problem isn't impossible anymore. And that kind of brings us to one last thought. This whole powerful technique, from the step-by-step recipe to the high-speed formula, it all came from that one simple, elegant guess. y2 equals v of t times y1. It really makes you wonder, doesn't it? What other huge, complicated problems in math or, anywhere are just sitting there, waiting for one clever guess to crack them wide open?